Welcome everybody to the 4th edition of our online show TPRC Talks. My name is Aniek van Damme, and together with me in the studio are guests that are very excited to share their interesting experience with you. So, live from our lab in Enschede, we once again invite you along into the world of the Thermoplastic Composites Research Center and talk about how our research contributes to build lighter and more sustainable aircrafts. Well, in these talks, we talk about how our research is helping in this way, and you can rewatch all the TPRC talks on the TPRC YouTube channel. This episode is a follow-up on TPRC Talks 3 on welding. Last time we explained that to realize larger and more complex structures, we need to weld. But we can't weld everything. Therefore, we're now talking about melting or joining, welding, combining in any way different materials together. And to do so, the right connection, the interface, is very important. My first guest here is Sebastian Wijskamp, Technical Director of the TPRC. Sebastian, can you tell us a bit more about your role and why we are talking about this subject?
Hello, Aniek. So my main responsibility is implementing the research roadmap that has been devised by our industrial partners together with the scientific team. Why we talk about hybrid joining today, about multi-materials, is that, as you mentioned, we have looked into thermoplastic composites in general. We've looked into stem forming in very much detail. We've talked about welding, all in all to make thermoplastic composite structures. But in the end, we know, although we really would like to, aircraft structures or cars will not be fully thermoplastic composite. So we need to join our beloved thermoplastic composites to other materials.
Well, we are very curious whether you are a multi-material joining rookie or an advanced professional. So in the next few seconds, I invite you to fill in this poll. Yes, are you a multi-material joining rookie or an advanced professional? Yes, we have the results here already. Sebastian, well, that's quite clear. What do you think?
I think it's a nice mix. So we have, I think, enough rookies to continue with the show, and also some more advanced level experts that probably can ask us some very interesting questions for further discussion later on.
Well, talking about questions, if you have any questions about this topic or about the TPRC in general, don't hesitate to share them through the Q&A, and I will make sure there's room answering them in the last part of the show. Well, Sebastian, why is it important to connect different materials together? In other words, what's the benefit of this multi-material joining?
Well, in the end, you really would like to have the right material in the right place. So combining different materials, metals, composites, plastics, is really needed to take lightweight design a step higher, further. If you look at modern aircraft, they have 50% thermoset composites. The other half is advanced metals such as titanium. And if we want to integrate thermoplastic composites, we need to be able to connect them to these other materials. And of course, we can also always do that by drilling holes and fastening. But at the TPRC, we like to take it a step further and really try to do that without bolts or adhesives.
Well, next to the aerospace industry, in what other markets do you see business developments?
The automotive industry, for example, is very well known for multi-material design. So they have been able to blend, to work with different grades of steel, magnesium, aluminium. Glass and carbon fiber reinforced composites have been making part of the structure and other parts in the car as more and more. When the share of composite grows, we also need to think of recycling, and that's where thermoplastic composites come in. It can be a very interesting material for the future.
And in what way do we see this material being used in cars already?
And mainly in hang-on parts. Can be car seats of the car, can be beams, front-end modules, so where steel parts can be relatively easily be replaced by composite parts.
And with what materials can you join TPCs with then?
So in the car, you would like to join with, for example, steel or aluminium. In the aircraft with titanium or aluminium. But also, for example, in the wind energy, you would like to join thermoplastic composites with vinyl esters or polyester composites.
So in the wind energy, in the energy industry, in what way do you see it manufactured there?
Now, we've been dreaming of full thermoplastic composite blades for a long time already. But we also see that it's quite difficult to make them fully thermoplastic, cost-wise, maybe technology-wise. So there we now see a trend towards only placing thermoplastic composites on very specific parts, like say the wing leading edge, the blade leading edge, to shield it from rain erosion. For example, at the University of Twente, some research is being done there already.
So the interface between those two materials is very important, and TPRC is focusing on this interface. I can imagine that engineers are not always aware of the difficulties that come with that. Can you identify these difficulties?
The difficulty with the interface is it's not really a thing. So it's there. It's there where one material ends and the other one starts. With the individual materials, we know very well how to cope with them. We can take a piece, we can put it in a test bench and determine what is the material strength or stiffness. We can make material models, we can write handbooks and guidelines for the individual materials, but this interface it's a thing happening on the micro scale or even on the molecular scale, and we cannot really take the interface and put it in a test bench or an analysis tool. Most of the times we have to test the connection itself and then kind of reverse engineer to get an idea of the properties of the interface. And these properties really depend on how you manufacture the joint. It's really process dependent.
Well, talking about joining, one of the ways of joining is injection overmolding. And therefore we invited this promising TPRC talent. Welcome, here he is, Jeroen Houwers. Hi.
Thanks, Aniek.
Hi. You work as a research engineer at the TPRC. You're a pioneer in this field of study. What's your research all about?
During my studies as a mechanical engineer, I joined the solar team Twente, so we participated in the World Solar Challenge, and we drove across the Australian outback for 3,000 kilometers. And my job during that time was to work on the lightweight composite body of our solar car. And I got really enthusiastic about the properties from composite materials. So during that time, I also learned that TPRC was a great place to dive further into composites. So when I graduated here at TPRC in 2014, I'm still very happy that they offered me a job then.
Yeah, so just to interrupt, Jeroen, there were 4 engineers already from the Solar Challenge team, right?
Yeah, indeed, yeah.
So to us, it's very important that they are here because they are the ones that are actually experienced with composites.
Yeah, definitely.
So what is your research about then? What do you study?
The overmolding of thermoplastics is a relatively new process, and it basically combines stamp forming and injection molding into a single process. However, there's still a bit of a knowledge gap to prevent the adaptation in the industry. And to bridge that gap, we started the COMPETE project in 2015, and to bridge this. And overmolding is a multi-material process. So at the interface where those two materials meet, there's lots of interesting things are happening there. And one of the topics that we're researching here at TPRC is how to predict and also how to characterize the interface between those two materials.
So the scope of your research is predicting the interface strength, right?
Yeah.
What tools or material data do you need for that?
Well, I think we have a very nice video about this. So
let's have a look.
My name is Jeroen Houwes, research engineer at the TPRC. Today I would like to tell you about the research into overmolding. Overmolding is a hybrid process which combines stamp forming and injection molding together into a single process. Within a few minutes we can transform this sheet into this compact part with integrated ribs and features. As a part designer, you can combine the strength of the thermoplastic composite sheet together with the design freedom of the injection molding process. However, there's still a knowledge gap to overcome to adapt this process in the industry.
In order to reduce the number of iterations needed and get first-time right tooling, we rely on a variety of simulation software packages, such as that from Aniform and Autodesk Moldflow, which we then couple together to simulate the whole overmolding process. The final step is to perform a structure analysis, which validates the simulation by comparing the results to the mechanical performance of an actual part. We're also researching the interface strength of different material combinations by performing tests on overmolded samples with different parameters. The aim of this is to standardize the process and, in the end, share the resulting datasheets with our partners.
Andres Garcia, what did you bring?
Well, this is the complete demonstrator from our video. And what I'd like to show you today is, if you look here, for instance, here at this place, and if you look under the microscope, if you make a cross-section out of it, then you can... perfect, you see the picture on the screen now. What you see here is on the top, you see the injection molded compound, and on the bottom you see fibers. So what's happening here is that the fibers from the laminate are partially within the injection molded cavity. And this is what we're calling fiber migration. And what's happening is that during the process, we heat up a laminate above its melting temperature, and then we place it in the injection molding machine, and the injection mold closes, and at that point the laminate reconsolidates. But at the locations where you have those ribs, you don't have any pressure at the moment. So what happens is that the fibers are pushed in the cavity, and we know that this fiber migration it promotes the interlocking of the compound and the injection molding compound and the fibers, so it makes the bond a bit stronger. But on the other hand, it also influences the compression strength of the laminate. So there's a trade-off to be made, and we're working on tools how to check and develop how this fiber migration can positively or negatively influence your part.
Well, when it comes to injection molding, we do that for ages, right? Why is this still a topic?
Well, there are two ways to look at this. So one way you can see overmolding as a method of increasing the strength and stiffness of a regular injection molded part. So you can place locally a insert in the part. Or what you can also think of is enhancing stamp forming parts. For instance, this demonstrator here, we have a stamp form part, and we can enhance this part by adding these ribs and features. And you can also think of mounting points to ease the assembly of the stamp form parts. So there are multiple ways how you can use overmolding in your process.
So we've talked about the aerospace industry, we talked about the automotive industry, but there's a lot more potential, right? Battery boxes, gearboxes, electronics. What's the potential here? Well,
overmolding has a huge potential because it allows to manufacture light yet strong parts at a very high volume, and they can also be quite complex. So, for instance, battery boxes of electrical cars. You need to have a strong structure to hold the weight of the batteries, but you also need to have mounting points for the batteries, for electronics, and the design freedom of injection molding may allow you to use to create this part in a single process where all these features are already in there. And you may also think of enhancing the airflow for better thermal management, or If you think a bit more in the future, for urban air vehicles, so electrical taxis, weight is even more critical, and you have the same sort of problems in automotive. So I think there's a huge market for overmolding here.
For the mobility of the future.
Definitely.
Yeah, right, great. Well, Sebastian, on a broader perspective, why is this research so important, and how do you collaborate with partners in this?
So the importance is two things. One is we're still, I think, not fully exploiting the full potential of injection molding. So we're making nice parts with ribs, but injection molding has been there, as we just said, for a long time, 80 years. The most beautiful things can be made with injection molding, the most smart connection types and so on. So that's something that we can transfer to composite technology as well.
Yeah.
And of course the process robustness and how to handle mass production. That's in this industry a common thing already. The other thing is that and this is something that we're going to tackle in the next phase of the overmolding project at the TPRC. If you look at the fundamentals of the interface, the fiber migration Jeroen discussed, how the evolution of the structure influences the performance of a part. That is something that will be researched in the big project called Enlighten. We also mentioned last time. This is a large project where 4 universities work with 13 PhD students on, say, the process structure performance relationship of welded and injection overmolded parts.
So big topic for the future as well.
Yeah, so there, I say engineering at the TPRC, fundamental research at the universities go kind of hand in hand.
Well, you must do that with the collaboration of partners, of course. Yeah. What partners are important to you?
So that's, of course, our own TPRC members. But the Compete project, in that sense, was a special project to us, because also additional partners could participate in this project. So not joining TPRC, but joining the overmolding project specifically. So with the most recent phase of Compete, we work together with Safran Composites, with Trenzeo, with Autodesk Mold Flow, and the National Composite Center, for example.
Well, talking about Autodesk Mold Flow, well, in every TPRC Talks, we invite people from around the globe to talk on this topic, relevant partners. And today we have Franco Costa from Autodesk. Hello, Franco.
Hello,
hi,
Annie.
welcome. Hi. Hello.
Hello, Annie.
You are Research Director for the Autodesk Mold Flow product family for the company Autodesk. You're in Melbourne, Australia. It's a bit after midnight for you, so thank you for being with us at this time. Can you tell us a bit more about Autodesk and where you fit in the organization?
Sure, Annie. Well, Autodesk has a broad portfolio of softwares for different engineering purposes. And mostly they're centered around aiding design and aiding users to bring their designs to realization. And this is across a broad range of industries. You might know Autodesk software in the construction industry, media and entertainment industry, but also primarily the area I work is in the product design and manufacturing industries. And in particular, our focus is around design and make. So not just a CAD design package, but also tools built into that to help our users realize the manufacturing processes of their parts. And so, there's milling operation software, there's various other softwares for manufacturing. But the one that I'm focused on is the injection molding simulation software, injection molding and compression molding processes. And this is the mold flow software, which is now part of Autodesk, has been for many years. So for injection molding simulation, for injection molding simulation, our philosophy of the simulation is to make it accessible, to make the software tool something that's understands the manufacturing process and gives guided results towards the users of our software, and provides the material data necessary for that simulation product. So it's kind of, we're aiming to give a total package there.
Mm-hmm. And related to the Compete project, can you share some learnings with us, the biggest learnings in this?
Sure. Well, coming into the Compete project, what we were looking for was some industry-specific knowledge about composite overmolding processes and the design philosophies behind that. We, because of our injection molding experience. We didn't necessarily know a lot about the composites. So what we've gained is, through this Compete project, is an awareness about the physics, about what's happening in that manufacturing process, the issues of fiber migration that we've already heard about today, issues about the remelting, the importance of considering the ply directions in the designs. These are really important factors that we didn't know about prior to coming into the Compete project, and we've learnt from the project. The other thing that's been useful is the validation case studies that we've been able to use to demonstrate that some of the assumptions that we've made in our simulation of composites overmolding are valid and that we're heading in the right direction.
Thank you. You already shared some benefit you had from this collaboration. You're a special partner at TPRC because you're only part of the single project. Can you share some benefits on a company level?
Well, for us, it's been the process, the industry knowledge and the process awareness. What we've really appreciated about the TPRC's experience that it's brought to us is the practical knowledge about the process that we didn't have. And also, of course, the collaboration with the various industry partners means that we've been able to form those relationships, show them what we can do with our software and learn about their needs for the software as well.
Thank you very much. Interesting. Thank you for sharing this story with us. And if you have any questions for Franco or for Jeroen, all partners will join the Q&A at the end of the show. So share your question through the chat. Sebastian, in what way do you benefit from Autodesk?
Yeah, we started from scratch more or less in 2015. So Franco and colleagues have been a great help in starting injection molding. So on the modeling, but also on the practical tips and tricks. We like their simulation approach. So having the right models, but more importantly, fed with the right material parameters. And I think Franco has been a great help steering us, keeping us on track. If you leave it to engineers or scientists, we can go totally crazy with all kinds of material models and complicated analysis techniques. But he made sure that those analysis techniques are also commercially exploitable and not overly complicated, just good enough.
And how does that work? Because at a certain point, you sit down together and you focus on the outcome of the project together with Autodesk. Mm-hmm. How do you start from scratch and ending up in this relevant topic?
This is also a process of iteration. So having a basic direction, trying things, evaluating results. We have regular meetings for that, workshops in our place. It's just it feels like you're with your colleagues, just working on this project.
But then on the other side of the world.
Then on the other side of the world. And it was, we had to manage also with North American partners and Australia. Also with summer and winter time, this could lead to some funny meeting times.
Okay, thank you. Well, in the meantime, Vanessa Marinoshi joined us. Welcome, Vanessa.
Thank you, Annick.
How did you get involved with the TPRC?
Well, let's say it all started about 5 years ago when I was still a student. And I moved all the way from Italy to the Netherlands to do my master thesis in GKN Fokker. And that was such a positive experience that I really wanted to continue to work in this field. So first, I was at the National Composite Center in Bristol to work over there as a research engineer. But after some time, I realized that I wanted to challenge myself even more, maybe with a PhD program. And at that time, the TPRC gave me this opportunity. And so now I'm here, and my research focuses on interfaces between metal and thermoplastic composites.
And what is it that sparks your passion about this?
Well, there are so many challenges and knowledge gaps, and that's what's the fun.
You really like a good challenge, quite ambitious, very nice. When we talk about injection overmolding, we talk about we have two materials based on a thermoplastic polymer. But when your research comes in, it's totally something different because it's about TPCs bonding to metal, right?
Yes.
Because your project is called the ECOMOLD project. Where does that stand for?
Yes, which stand for efficient comolding of metal thermoplastic composite hybrid joints.
Well, let's have a look at your video.
My name is Vanessa Marinosci. I'm a materials engineer and PhD student here at the TPRC. My research is on metal thermoplastic composite hybrid joints with a focus on the interface. Currently, the standard joining techniques imply the use of mechanical fasteners or structural adhesives. But when using thermoplastic composites, we can think of a third joining technique, which we call the co-consolidation. With this technology, we can join directly thermoplastic composite to metals during a standard composite consolidation or forming process, because at high temperature, the thermoplastic matrix melts and acts as an adhesive to the metal. An example of a final product that we can obtain is a fiber metal laminate, in which, as you can see, layers of metal are alternated to layers of composite, resulting in a material with superior properties, such as high environmental and high impact resistance. Or another example can be a hybrid structure like this, in which a metal insert is already integrated into our composite structure. Therefore, this co-consolidation technology can potentially replace standard joining techniques, which are typically time and cost-consuming. To make this co-consolidation a reliable technology, the key, but at the same time the challenge, is to have a proper understanding of the interface. Here at the TPRC, in order to tackle this objective, we are sharing our expertise with the expertise at the University of Twente. In this project, I collaborate together with Yorgos, another PhD student, in order to approach this interface in a multidisciplinary way.
In the metal surface preparation, prior to the joining process, we form thin films inspired by nature and more particularly sea organisms such as mussels that are able to strongly bind on any surface even at harsh conditions. By incorporating different molecules in these nanolayers, we can tune their chemistry and result in stronger and more durable interfaces. By optimizing the processes in the nano and micro scale, we can maximize the performance of the joints on the macro scale. The aim of our work is to develop an essential and industrially relevant knowledge building block.
Conducting research on interfaces means not just working on a part level, but also on a sample level, which is then mechanically tested. The preparation of these samples is made here at the TPRC using standard composite consolidation processes, such as autoclave or press forming. And afterwards, these samples are tested at the University of Twente, where interfacial properties such as Mod 1 or Mod 2 fracture toughness are evaluated. Mechanical testing is always followed by an analysis of the failure mechanism, which is typically carried out using different microscopy techniques. Finally, our experiments are of input for a numerical model, which enables to predict the mechanical performance of the interface given certain surface conditions. In collaborating with Yorgos, we learn from each other, and that allows us to share more knowledge with the TPRC partners.
So Vanessa, this co-consolidation technique, do we see that already on the market?
Well, not yet, but we do see that in a lot of applications, composite and metals are connected together. And this is currently done with well-established joining technologies such as mechanical fasteners, structural adhesives, or a combination of both. But since thermoplastic composites are gaining more and more attention, then we can exploit the moldable nature of the thermoplastic resin. And therefore, we can think of this co-consolidation technology as a potential replacement to the standard joining techniques, because co-consolidation, consolidation of the composite and bonding to the metal are achieved in one step. And this, of course, will save time and cost that are typically related to the normal and standard joining technologies.
So what do you think will be the first moment that we see this implemented?
Well, difficult to say at the moment because there are many challenges and knowledge gaps.
And what are the main challenges?
For example, at this stage especially, the most important and the biggest challenge is the interface. Because every time we deal with a new or a different material system, every time we have a new interface with different bonding mechanisms that can occur over there. So if we don't understand and control this bonding mechanism, there's a high chance that the interface is the weakest link of the overall structure. So in order to make this co-consolidation reliable, the main goal of our research is to build a fundamental understanding of this interface. And we are doing this from different point of views, which of course involve different fields of expertise and science. So from one side we have Yorgos, who is investigating the nanoscale level, so the molecular interaction between metal and thermoplastic composites. And from the other side there's me, who is investigating the macro and microscale level of the interface.
And what do you see happening on a microscale level?
Well, at the microscale level, for example, we have already an important bonding mechanism that can be promoted between these two materials, which is the mechanical interlocking. And we can promote this sort of bonding mechanism by treating the metal surface prior to the co-consolidation step. So, for example, we can create surface irregularities or cavities that can be filled by the polymer at high temperature, thereby making this interlocking.
Can you tell something about this?
Yes, so these images, for example, is a summary of one of my recent papers, in which I indeed investigating the effect of this mechanical interlocking, specifically between titanium and carbon black, which is manufactured with this co-consolidation technology.
So how do you look at this technology for the future?
We are finding out that there's definitely potential in this co-consolidation technology. We managed to achieve quite a strong and stable bond between metal and thermoplastic composites, but of course this is just the first step. There's still a lot to do, and this because in order to build this knowledge of the interface, we mostly worked on a sample level, but now all this knowledge that we build on a sample level should be moved to a part level. So it will be wise to start to work with parts that look like more real structures. And maybe also here start simple with secondary structures, see what are the challenges over there and how the structure responds mechanically, and then eventually also move to primary structures.
Interesting. Sebastian, from your perspective, how do you see that?
I totally agree with Vanessa, of course. So technology demonstration on the macro scale, that really goes hand in hand with fundamental understanding on the nano or molecular scale. You have to try things on the part scale to find out what works or not. Otherwise, maybe with some interface development, you go into a certain direction, but it cannot be implemented in a real production situation. So that's iterating between these scales.
So, and in what way do you collaborate with other fields?
As we saw, we need Yorgos for chemistry, and this with the polymer materials science group and for chemical engineering. We really need to understand the surface, not only from a chemical point of view, but for example from a mechanical engineering viewpoint. Then we work very closely together with the surface engineering and maintenance group of the University of Twente, and that's, as we saw with previous talks, where we work together with electrical engineering for induction welding. We have access to all these disciplines here at the University of Twente, and the knowledge that we do not have directly within
in-house,
the TPRC,
yeah.
we can use the university there.
Nice. Well, we have Matthijn de Rooij joining this show. He is Professor Surface Engineering and Maintenance at the University of Twente. Welcome, Matthijn.
Yeah, thank you.
Hello. And you're
Hello.
also the supervisor of Vanessa, right?
Yeah, one of them. She has multiple supervisors.
Okay.
Also Sebastian.
How proud are you when you hear her talking? How proud are you when you hear her talking?
I'm very proud. I mean, I think she explained things so carefully that, well, what can I say? I think she did it very well so far.
Great.
Yeah, very nice.
Can you tell us more about the Surface Engineering and Maintenance Group at the University of Twente and your role within that?
Yeah, let's say services and interface are, of course, very important to us, as the name already indicates. It's not just composites. Service and interfaces everywhere, and they often need special attention in some way. And we have 3 types of interfaces we study. Some interfaces are supposed to move, like hinges or bearings, and then you want to often separate them with lubricants or reduce friction, and this is the field of topology. This is more or less the foundation of the research group. And the other extreme, you have interfaces that should not move, like the ones from Vanessa. They have to stick together. So then you talk about joining, where you want to join surfaces together and to make them more reliable, to understand them better. We've also assistant professor working on that, Jamal Sanjani. And also interfaces that are on the edge of moving. Interfaces, for example, in positioning mechanisms, but also in earthquakes, very different, which is actually a sliding phenomena in faults in the earth crust. And they also work together on geologists with University of Utrecht. And so it all looks very different, but actually there are lots of similarities. In all cases, you talk about surfaces interacting, and I think you can learn a lot from each other, from all these different fields.
Mm-hmm. And can you tell us a bit more about in which areas you collaborate with TPRC?
Yes, well, of course, hybrid structures with Vanessa, but also before that, we already worked together with Yibo Su on hybrid structures. We also worked together with Lang Yong, who worked on anti-sticking between a mold and a composite material. But also soon we will start another project, not with TPRC, but with Tijin on aerometer ropes, where all kind of fibers interact. And of course, this knowledge can also be used again at TPRC, because interaction between fibers will also be very important for composites in the end. So it goes 2 ways, I would say.
Nice. Well, when we talk about multi-material joining, how do you look at the future?
Well, it has already been indicated that interfaces are very, very complex. I've already mentioned several times. So I think that the focus should be on making them more reliable and predictable. Let's say properties of materials are known to some extent, but this is not true for interfaces. And you have an interface. If you join materials together, you always have interfaces. So there's not a lot of things known at this moment, and it's really important to understand these interfaces better to make them more reliable and predictable. This is, I think, very, very important for the future.
Thank you very much for your contribution, Matthijn.
Yeah. Thank you.
And please note that Matthijn will stay for the Q&A. So if you have any questions for him or for Vanessa, Sebastian, please share them now. Now is the moment. Well, Sebastian, when Matthijn was talking, I saw you nodding when he came to talk about his project that he did with another partner, but where you also can benefit from. Can you talk about that for a second?
Well, it's a general fundamental knowledge created, and that's also, say, in art to take. And that's a nice thing also with fundamental knowledge that is still far away from the application. You could take some knowledge created in one project and use it somewhere else. So go from, fibers and matrices. So composites in general, that's all about the interface between a fiber and a matrix. And we're also kind of using that kind of interface technology for titanium to pack bonding, for example. So, it's gathering fundamental knowledge from all these different disciplines.
Well, I'm curious. I mean, we've talked about injection overmolding. We talked about joining TPCs to metal. But what other future projects are you focusing on?
So maybe where a couple of years back we would say thermoplastics, you can weld them or co-consolidate without any adhesives. We also see that joining of thermoplastics to, for example, thermoset composites by adhesive bonding, that's also a topic that we need to address. for structural design, so multi-material design, making even lighter composite structures or integrating thermoplastics into an existing thermoset part. Or, and maybe even more important, for structural repair of thermoplastic composites. So we've started last year a project on repair, still scoping what we can do there. Of course, being thermoplastic composite fanatics, we would like to use thermoplastic composite technology like welding or co-consolidation. We also see that maybe on the short term, using more conventional thermoset repair technology is better. So then we, with thermosets we need to co-curing or adhesive bonding could be a good solution. But then we may have to make sure that we can stick something to a thermoplastic. And we've selected the thermoplastic composite materials that we are using because they are very inert, not reacting to any aggressive liquids. But it also comes with the disadvantage that you cannot, glue will simply not stick. But if we understand how we can manage the surface of the thermoplastic composite, we can kind of stick it to any other material.
Interesting, right? Because when you talk about repair, it also matches the bigger picture of sustainability.
Yeah.
And the future, of course.
Yes, you don't want to throw away big parts. You want to make sure that you can repair locally.
Yeah.
Yeah.
Do you already have somebody within the TPRC that's going to focus on this project?
Yeah, that's a nice one. For this specific project, we are going to work with an engineer from one of our partners, and he's been granted a scholarship from his company, so he can spend 4 years abroad at the TPRC to work on his PhD on this specific topic.
Nice.
So that's also a way we like to cooperate with our partners.
Then you have a win-win-win situation.
Yes, we get so it's an experienced person. We get a good engineer working on a project. He will graduate with a PhD, we all hope, and the company gets back a PhD level researcher with also lots of experience in another country, in another culture, but also working with all these experts here at the TPRC.
Well, talking about partners, we have another special guest from the industry. We have John Grasmeder, Chief Scientist of Victrex. Hello, welcome. You're in the UK.
That's right, Aniek. Hello.
Hello, welcome, John. Victrex is a supplier of PEEK-based polymer solutions. You got involved at the TPRC within the COMPETE project and now being a full member of the consortium. Can you tell us more about Victrex and your role in the organization?
Yes, of course. So, as you said, Victrex is a world leader in high-performance polymer solutions, and in particular, PEEK and polyarylether ketone-based materials. We focus principally on 5 markets: automotive, aerospace, energy, electronics, and medical, where we've got over 40 years of developing solutions with these materials. But we don't just make the polymers. We also produce a range of semi-finished and finished products, including composite tapes, laminates, and overmolded components, as well as films, fibers, gears, pipes, and medical devices. To my role as Chief Scientist at Victrex, I have a broad scientific remit, principally covering chemistry and materials science, but also increasingly data science, modeling, and simulation. Part of my role is to develop and deliver our strategic research interests and capabilities. Our activities in composites across multiple markets is an example of that. Additive manufacture is another. So I work as part of the wider Victrex team with customers, with end users, with academic partners, to generate and deploy the science which supports finding those solutions that meet our customers' needs.
Well, when we talk about injection overmolding, research related to the COMPETE project, what did you contribute and what did you learn?
So I think what we contributed was our experience in the PEEK and polyarylether ketone-based materials, particularly formulating and processing them. We supplied the materials which facilitated the overmolding process. So on the one hand, there was the new low melting PAEK, which was used in Torre's C-Tech fabric. And on the other, there was the high modulus injection molding compound, Victrex PEEK 90HMF40. And I think working with the TPRC was a great opportunity for us to learn and to accelerate the overmolding process development and background understanding. And as Sebastian and Franco mentioned earlier, I think I found the TPRC's hands-on experience being used alongside the modelling and simulation approach to be a particularly powerful and effective combination. And in addition to that, of course, we gained access to and generated a wide range of data on material and process parameters. And of course, that helped us build up the guidelines for the overmolding process that we have today.
Nice. And you already talked a little bit about this, these benefits. Later on, you became a complete TPRC partner. Can you explain a little bit more about the benefits for your organization?
Yes, so I mean, our experience in the first part of the Complete project convinced us that it would be valuable to become a Tier 1 member of the TPRC. And as I alluded to a moment ago, access to expertise that we didn't have within Victrex was clearly a key factor. But perhaps most important was that with the TPRC, it enabled us to collaborate with the entire supply chain at once, you know, from the equipment and machinery manufacturers through to the component and system producers, all the way to the end user. And without the TPRC membership, these interactions may have been a lot more sequential or very much more limited, and that would have limited the pace of technology development and the adoption of this new technology in the marketplace. However, when we work as part of the TPRC consortium, we're all focused on a series of agreed common projects and goals. And that means we can work on things in parallel across that supply chain, so the feedback loops are shorter, the communication's clearer, and the iterations faster.
Well, thank you very much, John, for sharing this story. We'll see you in a minute for the Q&A. Thanks very much. Sebastian, what are the options for companies that want to start using multi-material joining?
We can work in bilateral projects, or companies can join as a partner, as John just mentioned. Then you also have the access to the rest of the expertise and the network, of course.
How can they contact you?
Just reach out. I think the email address, phone numbers are there.
Okay, yeah. Great. They'll know how to find you.
I hope so.
Very good. Well, in the meantime, the questions have been brought to me. It's time for the Q&A. The first one is from Barbara Mabet, and this one is for Jeroen. Hello. Is it possible to apply local overmolding on a very big part like aeronautics?
Aeronautics.
The handwriting of my assistant. Okay. When it comes to fuselage or wings, what are the initiations of overmolding?
Yeah, well, in terms of very large parts like fuselages, the overmolding process, you need to place a mold in between. You need to place a part in between a mold. So if you have an extremely large part, I think there might be some technical difficulties there to fit this very large part into the overmolding machine. So they are quite big size injection molding machines, but they go up to maybe 2 meters, but maybe a bit more. But I think that's about the limit of part sizes you can get at this moment. So in theory, yes, but practically the machinery is not there to accommodate this local reinforcement by overmolding in a fuselage structure.
Clear. Something to add to that? A short thing?
Yeah, I think I have seen some technology where you could, place an injection nozzle onto a structure, but then in the end you have to generate a clamping force.
Yeah.
And then I think fuselage shells are really, really big.
Well, the next question is for you, Sebastian, as well. It's from Amir Esmaili. What is the substrate material and overmolding material used at Jeroen's project, Compete project? Maybe you can answer this one together.
The material, so yeah. We've used the Victrex material, so that's the 90 HMF40, so it's a peak filled with 40% of short fiber carbon fibers, and it's an easy flow peak, so it's relatively easy to process this at the processing temperature. And yeah, we also used other materials, PPA, for instance, or polycarbonate is also...
PS6 in the beginning?
Yeah.
PS6 as well.
Can you tell a bit more about that material?
Yeah, that's more of an automotive grade, and yeah, not too much to tell, I guess.
Okay.
It works really well. I think it was kind of the standard already for injection overmolded. So injection overmolding, we used that in the beginning, and then we gradually specialized in the more advanced material systems like the polyaryl ketones that John also mentioned.
Well, let's go to Franco Costa from Autodesk. We have a question for you, Franco. What are the current? Yeah, okay. What are the current trends in injection molding simulations? Faster, more complicated, big data handling? What trends do you see?
Well, I think the value add of more complicated is something that's been happening for many years. That multi-process overmolding of different metal inserts, composite inserts, or overmolding of a previous injection molding, some of it happening sequentially in a mold, are all value-added processes that the complexity of the injection molding is increasing greatly. Also then, from our point of view, we also see an increasing requirement in design accuracy and simulation accuracy. I think the tolerances are getting tighter. The requirements and the performance requirements are getting higher. Everyone's trying to lightweight the design as much as they can and still have the performance. And so to do that, they need to be able to predict what's going to happen as well.
Finding that balance.
That's right.
Yeah, thank you very much. The next one is for Matthijn de Rooij from the University of Twente. Can you design the interface of a composite material like you can with a steel, with, for example, laser engraving?
Well, there are all kinds of techniques indeed to design interfaces. So you could indeed laser engrave a metal and bond it to a polymer, but I'm not sure if that's the question. It's about engineering a polymer surface. Is that the question, or?
Yeah. Sebastian is. So. We think.
Yeah. Well, there are also all kinds of techniques that you can apply to surfaces of polymers and of composites. But I think that, as I indicated, the level of maturity is much lower, I would say, of the knowledge that you have in terms of polymer interfaces than metal. So for designing, you need knowledge and you need to understand things better. So I think we are a bit more at this moment in the direction of research than design. That often comes later.
First things first.
First things first.
Thank you very much. The last one is for John Grasmeder from Victrex. What would be the typical applications for injection overmolding in the aerospace industry?
Well, good question. Generally speaking, smaller parts that are used in high volumes are good candidates for overmolding because although they're small, the volume of these parts contributes to substantial aggregate weight savings and cost savings on a single aircraft because there can be literally thousands of them on a single aircraft. So typical examples would include things like clips and brackets for pipes, cables, conduits, maybe secondary structure. But that's not to say that overmolding is only suitable for small parts. As was mentioned previously, in principle, you're limited only by the size of the injection molding machine. Victrex worked with Boeing and wrote research and technology and successfully developed and manufactured an overmolded panel which was 0.65 by 0.65 meters square as part of the rapid high performance molding program. And that composite panel actually achieved up to 45% weight savings compared to a part machine from aluminium as an alternative construction.
Okay, thank you. Sounds very promising. Thank you very much for answering these questions, and we're happy to answer the other questions one-on-one after the show. Well, this concludes our very fourth edition of TPRC Talks. I hope you all feel inspired. It's time to wrap up. Vanessa, when it comes to multi-material joining, looking back on the show, what do you want to highlight?
Well, I would like to highlight that multi-material joints is the right way to go if we want to manufacture structures as lightweight as possible in a cost-efficient way. But we have to bear in mind that when we deal with multi-material joints, we also have to deal with one or multiple interfaces.
And Sebastian, the last words are for you.
Yeah, but I think I talked about our little toolbox before. I think understanding the surface of thermoplastic composites, that's really a tool that we need. It will help us with hybrid joints, it can also help us with painting, with adhesive bonding, with welding as well. So we needed to even get more out of thermoplastic composites than we are currently doing. Even.
Nice ambition.
Yeah.
Well, before I start thanking everybody, there's one more thing. Because we are curious about your ideas when it comes to the next TPRC talk. The topic. Do you think we should talk about recycling, for example? Or do you want us to talk about advanced fiber placement? Or do you have another brilliant idea that you want us to discuss? Please fill in the poll, because we are eager for input. Thank you very much. Well, let's see at the results. Well, that's quite clear, Sebastian, for the next time.
That means homework.
Okay. Well, I would like to thank my guests, Vanessa Marinosci, Jeroen Houwers, Sebastian Wijskamp, thank you very much. And of course, the partners who joined, Franco Costa from Autodesk, Matthijn de Rooij from the University of Twente, and John Grasmeder from Victrex. Thank you very much. And of course, Yorgos Kapakoulos and Andres Garcia. Thank you very much. And if you have any interest in further discovering the benefits of thermoplastic composites, please do not hesitate to contact the TPRC. Thank you all for watching. Have a great summer, and we hope to see you on board at the TPRC.